So previously we looked at changes in rates of change. Essentially, in rates of change, we're really looking at slope. So what we're going to do is look at the difference between average slope and instantaneous slope. So average slope is basically the average slope, or the slope line between any 2 points. Okay, so we can find out the slope of that by using rise and run, whereas instantaneous slope would be represented by a tangent line. So if I want to find the slope right at that point, that instant, I would use a tangent line here. Okay, so those are the differences that we're going to do today. So we've got a parabola, and I want to find the average slope from x equals 0 to x equals 5. Okay, so I'm going to do the average slope here in blue. So here's my point, x equals 0, x equals 5, and I draw in my slope triangle. Okay, so I want to find the change in y compared to the change in x. Okay, so there's my slope. So the average slope from there, if I just count it, that change is going to be plus 5, and the change here is going to be plus 5. So the average slope from 0 to 5 is going to be, so right here, dy over dx is plus 5 over plus 5, which is equal to 1. So that slope, yeah, that looks like a 45-degree triangle, so the slope is 1 through there. So if I look at the average slope from -5 to 5, okay, the average slope from this point to this point, well, that's pretty easy. That's a flat line, so the change in y over the change in x is going to be, there's a 0 change in y, and there's a plus 10 change in x, so the slope is 0. And then the average slope from -5 to +2, +2 looks like it's right about here, so I'll do that in another different color. Okay, so from -5 to +2 looks like right about there. I'm just going to estimate that because I don't know if I'm going to get that exact. So I'm going to go across like that. Okay, that one is a negative slope. Okay, so it looks like it's -4, and the x displacement, it looks like it is +7. So the change in y over the change in x in this case is going to be down 4 across 7, and I'll just leave it as 4 over 7. Okay, so that is my average slope. So the average changes are going to be calculated like this. So we can do the same for sine. We're going to find the average slope. So this is sine 2x. Okay, so I'm going to calculate the average slope from 0 to pi over 2. When I look at that, there's my run, here is my rise, there is my slope. The change in y over the change in x looks like it's going to be +2 on the y over pi over 2 on the x, so we end up with 4 over pi as our slope. Just a little bit less than, looks like a little bit greater than 1 is the slope here. Okay, so from here to here, the run is pi. And if we look at the average slope from -pi over 2 to pi over 2, that looks like basically the average slope looks like it's the same slope as that. Okay, so, and I'll do it more formally, but really the slope is exactly the same. So I'm going to get +4 over a run of pi. So it's going to be 4 over pi again. Okay, so there is our average slope. Now, we also are interested in instantaneous slope. So instantaneous slope, this can be a bit of a problem because if we look at that tangent line to get the instantaneous slope, well, there's our point, and we can do our rise over run calculation to get slope because that's how we define slope, rise over run, and at that point, well, there's 0 rise and there's 0 run. So we get 0 divided by 0. And we know from our limits that 0 divided by 0 can be anything. In this case, for this particular 0 over 0, it looks like the slope is, I don't know, looks like it's about 2. Looks like we have a slope of about 2. Whereas, we can have a tangent line right there, and that slope is 0 over 0 again, but that slope is 0. So we have all sorts of different slopes that can be defined by 0 over 0. So this is a bit of a problem. So how do we approach calculating 0 over 0? Well, one way we can do is use a limit. So what we can kind of do is say this, and this is our argument. So the model here is we have a tangent line, the black tangent line at P. We want to figure out that black line. What we can do is we can estimate that slope of the black line, and we estimate that slope using this point here, Q1. And that blue line, we can calculate the slope of that blue line by finding the rise and run. Well, that blue line is not a very good estimate of the black line. So what we could do then is we can say, well, if that's not a good one, we can just move it a little bit closer and say at Q2, and we can see that that red line is, although it's not a good approximation of the black line, it's better. And we can even make a further argument then. If we know that if we're getting better as we move towards P, well, I can find a Q3, some point even closer, right about there. And that secant line slope is an even better approximation of that black line. And we can get closer and closer and closer, and we could use a limit to get to the 0 over 0 point, the tangent slope. And we have a process to do it. We have limits. We have limits that allow us to get to 0 over 0. It doesn't allow us to go there, but it allows us to see what's happening as we get arbitrarily close to that point. And that is going to then be our tangent slope. So as I choose a point really, really, really close to P, the slope of that secant line, which has a little bit of rise, a little bit of run, is going to be virtually identical to that black line, the slope of the black line. So this is our process. We're going to use a limiting process to do this.